What do 299,792,458 meters per second, 300,000 kilometers per second, and 186,000 miles per second all have in common? Now, I'll give you a minute on this one, or maybe more like a second, but it's possible you've already guessed it. They are all measurements. Measurements of the same phenomenon, the speed of light. In our universe, nothing can exceed the speed of a photon. Photons continuously move through space, and, at least in our cosmic neighborhood anyway, many of them originate from the sun. Now, beyond their role in sustaining life on Earth and aiding crop growth and helping us exist in general, photons also have potential applications in space exploration, namely through spacecraft propulsion. With no resistance in space, a lightweight spacecraft could be propelled by photons. This concept is known as the light sail. Light sails work just as you might expect them to. On the ocean, the sails of a boat catch the wind to generate movement. A small spacecraft can be equipped with a large sail of its own that allow it to reflect photons in one direction, which basically generates movement in the other direction. Such a spacecraft could move towards its destination with little or no fuel needed. Personally, I like to think this kind of thing could also pair well with, say, an ion drive for more potential long-term deep space exploration. But how did we get here, right? Where did the concept and idea of a solar sail start? For this, we must look back to the 17th century. Johannes Kepler observed that comet tails point away from the sun. He thought that the sun itself is what caused this to happen. In 1610, he would write a letter to his colleague Galileo Galilei. In it, here is one of the lines that he wrote. Quote, "Provide ships or sails adapted to the heavenly breezes, and there will be some who brave even that void." Unquote. It is possible that he had comet tails in mind when he envisioned this idea, but he wouldn't write books on comet tails until later, so we don't know for sure. There are several discoveries from following years that would continue to contribute and build up to the idea of solar sails in some way, shape, or form. Between 1861 and 1864, James Clerk Maxwell published his theory of electromagnetic fields. It is relevant here because it showed that light has momentum and thus can exert pressure on objects. In 1865, Jules Verne published the book From the Earth to the Moon. In this book, he included a line that described spacecraft moving more quickly than our current technology, and that light or electricity will probably be the mechanical agent. We shall one day travel to the moon, the planets, and the stars, can be quoted out of the book. While not direct, it is very possible that this is the first published recognition that light may be capable of moving ships through space. In 1899, Russian physicist Pyotr Lebedev, hopefully I said that right, was the first to successfully demonstrate light pressure. His measurements were performed with an arc lamp radiation, a vessel with torsion balance. This is essentially two small masses at different elevations that are supported on either ends of a beam. In this case, the masses were in a vacuum and were suspended on a quartz fiber. This very same light pressure is what we would use to propel a spacecraft with a light sail. Constantine His first name's not too hard. Sliosvowski? Konstantin Siolskowski? Wait a second. How is this said? Hold on, let's see here.
Константин Эдуардович Циолковский. Константин Эдуардович Циолковский.
Konstantin first proposed using the pressure of sunlight to propel a spacecraft through space. His suggestion for this was to outfit it with tremendous mirrors of very thin sheets to utilize the pressure of sunlight for momentum. This is somewhat reminiscent of modern designs. And hey, you know, the list goes on. Throughout the 1900s, various papers would be published on and around the topic of solar sails. I would say the last major push came from Carl Sagan in 1970, when he popularized the idea of sailing on light using a giant structure which would reflect protons. Just a short 6 years later, in 1976, the first formal technology and design effort for a solar sail began at NASA's Jet Propulsion Laboratory. The next question is, how does it all work? This is a photon. The sun emits an insane amount every second, which is what we see as light. Now, a photon has no mass, and as such, no weight. However, it does carry momentum. The force imparted onto an object by this momentum is known as radiation pressure or light pressure. You might also hear it called solar radiation pressure, I imagine especially in regards to the sun. And to reflect this, the sail used on the spacecraft should be as flat as possible to exhibit specular reflection at a high efficiency, ideally around 90%. I mean, I guess 100% would be ideal, but not realistic. Specular reflection means a surface can reflect light rays at the same angle that they hit the surface. A mirror is a great household example of this. Because they can reflect light in this way, the spacecraft can be moved in the desired direction. This brings up an interesting question, though. It is not enough for us to be able to use the momentum from photons. To truly reach any destination, we must be able to steer the spacecraft as well. So let's talk a little bit about attitude control. Listen, man, I don't appreciate the way that you treat us. I don't appreciate anything about you. You're horrible. Well, come on now, man. That's not very nice. You know, you should really learn to control your attitude. Not that kind of attitude control, guys. What we need is known as an ACS, or Active Attitude Control System. It is essential for a sailcraft in space to achieve and maintain its desired orientation. The idea here is that we want to be able to achieve a relative shift between the craft's center of pressure and its center of mass. And on top of that, in a direction of our choosing. There are a number of ways we currently can do this, such as altering reflectivity on the sail surface, movement or control of like a control mass, movement of individual sails, or control vanes. Space presents a challenging environment, and solar sails must be capable of surviving and operating under those conditions. The materials currently employed in constructing these sails often begin with a very thin polymer sheet, approximately 2 microns thick. For comparison, a strand of human hair is about 70 microns thick. This polymer sheet provides the sail with mechanical support. It is then coated with a thin layer of aluminum, which imparts the necessary reflectivity for the sail to function effectively. This design allows the sail to withstand the heat encountered during a close pass to the sun. And there have been other ideas suggested over the years as well, such as a sail made from carbon fiber, or part of a sail made from carbon fiber. In fact, the mission we are about to talk about seems to have combined these ideas a little bit. So far, we have taken a look at some history behind this idea, and touched a bit on why and how it works. Now let's look at an actual example, this time from NASA. So NASA has been developing new deployable structures and materials technologies to be used for sail propulsion systems, light sails basically. This type of sail will hopefully one day help us achieve lower cost deep space missions. It is currently being tested along with a CubeSat in NASA's ACS-3 mission, or the Advanced Composite Solar Sail System. Data obtained from this mission may not only help us with future deep space missions, but things like near-Earth asteroid recon missions, space weather satellites, or even communications relays for crewed exploration missions. ACS-3 is a 12-unit CubeSat, which is equipped with a solar sail. The CubeSat is around the size of a small microwave oven at 23 by 23 by 34 centimeters, 9 by 9 by 13 inches. And from within this space, lightweight booms extend out about 7 meters, or 23 feet, and they span the diagonals of the square of the CubeSat. These booms are what support the sail, which when fully extended is about 9 meters per side, or 30 feet. In this image, we can see just how big the sail is compared to the CubeSat that it originates from. The booms are made up of a carbon fiber reinforced polymer, CFRP for short. There's that carbon fiber I mentioned earlier. While the sail is made of polyethylene naphthalate? Naphthalate? Nailed it. Or PEN for short. With one side of the sail coated in aluminum for reflectivity, while the other side is coated in chromium to increase its ability to radiate heat away from the spacecraft. ACS-3 was launched on April 4th, 2024, aboard a Rocket Lab Electron rocket. The first goal for the mission was to demonstrate the deployment of the craft's 4 composite booms. These are what support its 860 square foot light catching sail, the one we saw earlier. And by August, they had completed this task successfully. Though their current configuration of the spacecraft isn't exactly ideal, the sail has extended out to its full size, but one of the booms appears to be slightly bent, which I'm going to try to put on screen. This probably happened when the sail and booms were pulled taut to the spacecraft during the initial deployment. According to NASA, this is not a big deal though, and the mission is able to continue as planned. NASA has listed 4 main objectives for this mission. Demonstrate successful deployment of the composite boom, as well as sail packing and deployment systems in low Earth orbit. Evaluate the efficacy of the shape and design of the solar sail. Characterized the thrust functionality of the sail as the spacecraft gradually changes orbit, and collect data on the sail's performance to inform the design of larger, more complex systems. And so yeah, the first one, they've already demonstrated at least the boom extension part of that. And you know, I'm very interested to continue to watch both how this mission goes and just the overall continued development of light sail technology. Solar sailing is still in its infancy. Including the mission we just covered, there are only a few in the books already, maybe around 3 to 5 total. So, for as long as we have been thinking about it, we have only recently really started testing it and being able to put it into practice. You know what they say though, one must walk before they can run, and you know, even crawl before they can walk. And in some ways, I think science can be similar. Each discovery built upon the foundations that came before it. Much like how the journey of solar sails has gone so far. Like I said before, I find myself excited to see just where this technology goes next and in the future. So what do you think of solar sails? Is there something I missed in this video that you would have liked to see? Leave it all in the comments below. I would love to see you there. And if you enjoyed this video, perhaps check out some more of mine. There's going to be one up on the screen here pretty soon, or it's already there. And if you enjoy them, who knows, maybe even hit that subscribe button. With that, let us all step outside tonight and look towards the stars. A spacecraft through space. Hey Google, basement lights on.